All right, so these are some density questions. So on table T, you have the formula um, density equals mass over volume. That's really messy. It's an equal sign. All right, so use that. And then also we have a whole bunch of densities on reference table S as well. All right, so I'm going to do something terrible, which is not read all of this, which you absolutely should, but I'm not going to. Then it says, calculate the volume in cubic centimeters of a diamond at 25 degrees Celsius that has a mass of 0.200 grams. Your response must include both the correct numerical setup and the result. So you got to show your work. Okay, so first of all, density equals mass over volume. We're talking about diamond. So look in the reading. So talk about the density of diamond. Diamond has a density of 3.51. 3.51, I'm going to put it over 1. And we're looking for volume, and so the mass is 0.2. So there's my correct numerical setup, but then it also requires a answer. 3.51 times V equals 0.2. Divide both sides by 3.51. V equals, plug it into your calculator, 0.05698 cubic centimeters. It did not tell us how to round. Maybe that's a few too many decimal places, but that's all right. All right. In the late 19th century, the Hall-Héroult process was invented as an inexpensive way to produce aluminum. In this process, aluminum oxide, Al2O3 liquid, extracted from bauxite, is dissolved in Na3AlF6 liquid in a graphite-lined tank, as shown in the diagram below. The products are carbon dioxide and molten aluminum metal. So they always love to teach you something during the Regents. It says compare the density of aluminum liquid with the density of the mixture of aluminum oxide and whatever that's called. Okay, so it looks like the mixture is up here, around, and it looks like the liquid is sinking out. So if the aluminum liquid is sinking out, aluminum liquid is more dense than the mixture. And you can tell because this process is undergoing and the aluminum sinks out. All right. 3 elements, D, E, and Q, are located in period 3 of the periodic table. Some properties of these elements are listed at the table below. A student's experimental results indicates the density of element Q is 2.10 grams per cubic centimeter at room temperature. And so you got some information. Identify the physical property in the table that could be used to differentiate the samples. So physical properties are things that we can observe, we can calculate, or measure. We can observe solid, but that's all the same. We can measure mass, but that's all the same. And density we could calculate, and look, that's all different. So density is what we could use. Number 4, determine the percent error between the student's experimental density and the accepted density of element Q. So according to table T, here's our formula. So the student, it said, had a density of 2.10, and then in the in the chart, it said the actual density is 2. And so over 2 times 100. So you get 5%. Okay. Sir William Ramsay is one scientist credited with identifying noble gas argon. Ramsay separated nitrogen from the air, reacted it with an excess of magnesium, producing solid magnesium nitride. However, a small sample of an unreactive gas remained with a density different from nitrogen. Ramsay identified it as argon and later went on to discover neon, krypton, and xenon. Compare the density of nitrogen gas to the density of argon gas when they are at these conditions. So I know because the reading did not tell me any information. I can go to table S. Table S. So it's going to be difficult to read this on the side, so just trust me here. Here's nitrogen, and here's argon. So here's nitrogen, and here's argon. So it looks like nitrogen is lighter. And if you couldn't read those numbers, that is okay because they were to the side. So you would just go to table S. And so you just say argon is more dense. And of course, you could also say nitrogen is less dense. But you have to compare them. You can't just say, these are the numbers. You should compare them. But also, you don't have to include numbers, as I did not. A glass sphere and a lead sphere each have the same volume. Each sphere is dropped into a container of water, which statement best explains why the lead sphere settles faster. Higher density. Glass sphere is a smoother surface. Lead sphere takes up more space. No. Density. It's going to make you settle out first. Okay. All right. So you have a whole bunch of information. And they're giving us mass and volume and density for some, and others we'll have to identify. So how about before we do, in part B, I know the density is mass divided by volume. So that's going to be 1.8 gram per centimeter cube. I don't know the mass, but I could find out. And then I can read the graduated cylinder for the volume. That's going to be 75 milliliters. That's a 5. I don't know. Do I need the mass? We'll see. The volume, we'll see if I need that. And then, well, I have a cube here, so it's going to be length times width times height. So that's going to be 15 times 2 is 30. So density would be 54 divided by 30. So 1.8 here as well. What is the volume of liquid C? We've already calculated that. It's reading a grad cylinder. What is the volume of object D? Okay, so we do need that. So density is 0.4. Put it over 1. Mass is 0.8. Volume. So 0.4 times X or V is 0.08. So divide both sides by 0.4. And that's going to be 2 cubic centimeters. Which two substances could be made of the same material? So we're looking for the same density. So 4, 1.8, 1.2, 1.4, 1.8. So B and E. Water W is added to the graduated cylinder containing liquid C. A and D were then dropped, which is most accurately shows. So obviously the most dense is on the bottom, least is on top. And you hopefully know that the density of water is 1.0 grams per cubic centimeter. So wherever W is, that's going to be a 1. Liquid C has a density of 1.2. So right away, A and B are going to be wrong because C is more dense, and so it would be on the bottom. So we're down to, and I don't know why I didn't copy, but C and D are right here. All right, so now we need to figure out, okay, so the cube A is 4. So this is a 4. This is a 4 here. And the sphere D is 0.4. So C is not going to work because the most dense item is not floating. The most dense item should sink, which it does in choice D. And is that it? Oh, so it is. All right, if you have any questions, please reach out. Thanks.